Okay, so thanks all for coming along to this sort of final talk in the series on the from the whole energy systems interest group here at Newcastle. We're delighted today. We've got Liyang Han from DTU. So Liyang Han is a postdoc researcher at the Energy Analytics and Markets Group at the Technical University of Denmark. His current research focuses on the economics of data with applications in renewable energy forecasting and other energy applications. Prior to coming to DTU, he received his PhD from the University of Oxford with a thesis topic on the application of cooperative game theoretic frameworks in prosumer-centric energy markets. He's interested in expanding his research on data markets to broader applications with metrics to measure the feasibility and fairness of such markets. So Liyang's going to talk for about sort of 30 to 40 minutes, and then, as I say, we'll have questions at the end. So Liyang, take it away.
Great, yeah, thanks Matt for the invitation, first of all, and also for the introduction. I'm going to try to share my screen now, and I hope you can see my presentation, yeah?
Yep, looking good.
Okay, great. So today's talk is going to be on my recent work on data markets, especially with the regression framework, and this, to be honest, has been a new topic for me, and I've only embarked on this journey, as you would call it, since I started my postdoc in 2020. And it's a quite new topic in general, and especially for energy applications. So before I go into the detail of the content, I would like to acknowledge that this work has been a joint work with Pierre Pinson and Jalal Kasimpour, who are my postdoc supervisors here at DTU. And we also have very close collaboration with some folks from Portugal in Escatec, Ricardo and Carla there. And also the work has been helped by Amandine, who is a PhD in our group as well. And the work I'm going to present today is part of the European Union Horizon 2020 project, Smart4S. So without further ado, I'm going to go from, first of all, an outline of my presentation today. I will first introduce why we need data markets as a motivation, and then dive into the detailed framework with the regression underneath the data market and how that is incorporated in the proposed framework. And then I'm going to talk about kind of the key points of this presentation, which is the allocation of the payment in the market. In other words, what is in it for the market participants. And based on how we're doing with time, I might or might not introduce some of the case studies that we have done, because it's quite a theoretical framework. So the case study results are very preliminary, and we have to have we only could use some like very preliminary data, and the results are also very theoretical. So it might not be that clear in the interpretation of the data. So based on the time, I'll see if I can have time to explain the case studies in detail. And before I conclude and talk about the ongoing research. So first of all, with the motivation, we, I guess most of the people here have some social media presence. And we all know that these social media platforms collect data from us, and then they resell the data to, other merchants for some monetary reward, and we get targeted advertisements as a result. Some people like those, some people don't. And the point here is that we all have different levels of comfort with our data being shared, and the fact that currently these platforms don't really distinguish our preferences, that is the problem. And there has been some measures that are put in place. For example, in Europe, there's the GDPR. I'm not sure if Brexit has had any impact on that being implemented in the UK, but I'm sure there's going to be, if not, some sort of equivalent method that is going to be put in place. And more in the energy context, we have asset management and also state estimation, where either the asset manager of a fleet of energy resources or the system operator have to use data to better forecast how they're going to reduce the cost and how they're going to operate the system. And these data sometimes are collected from entities that are different from whoever is going to use data. So sometimes it becomes a question of whether people are willing to share their data for these purposes, even though sometimes it looks like it's a win-win situation, but still people generally have this kind of privacy concerns about their data. So in order to encourage this data sharing and data usage, also while giving the choice to data owners, that is the kind of the point of us proposing a data market where people can actually set their individual preferences in these scenarios, so that and also they can be properly compensated for their data. And the use case I'm going to talk about today is on renewable forecasting. And here is a more detailed representation of the problem. So we have, for people who are familiar with the energy market, there are renewable plants, for example, a wind turbine that would self-forecast their production in advance and then bid into the foreign market, for example, a day-ahead market, and they get a certain contracted payment from that. And then in real time, their delivery is going to be different from their bid, and that would incur an imbalanced cost. And this cost is defined differently in different markets, but it somehow is related to the difference between their forecast and their delivery. And now if we have multiple participants in a market, there is a chance that they can actually, well, it has been proved in different literature that there is an opportunity for them to share their data and help each other improve their forecast so that they can have a better position in the market or have some sort of saving or reduction of the imbalance cost in the market. So it sounds like a win-win situation, but the problem is that there are also competitors in the market. There is an intrinsic kind of unwillingness to share their data just because of this competition that exists between them. So this is why we thought of the concept of a data market where we can have a system in place that, first of all, guarantees a certain level of privacy for their data to be shared, and second of all, it could help each other. It could help the wind agents in the market to improve their forecast mutually. So here is a detailed framework of our proposed framework. But before I go into the specific kind of explanation, first I want to introduce some of the existing work that has been done on data markets. In recent years, there has been quite a few frameworks on data markets that have been proposed in the literature. These are some of the examples, not necessarily applied to the energy context, but data prices, fair allocation, and privacy have been looked at by a certain number of people, and also competition among data buyers also has been looked at using game theoretical frameworks. But the properties that we're looking for here and in this work that I'm going to present are the following. The first one is the balanced budget of the market. That means that the total payments of the buyers will be equal to the total revenues of the sellers. And secondly, we have to guarantee a replicability of the market, meaning that no matter when you come into the market as a buyer, as long as the task is fixed, as long as the data available are the same, you would get the same outcome of the market, and all of the sellers will be paid the same. So it's independent of the time of the trade and also the order of the trades. In some other works, there has been cases where if buyers come in at different times, they would actually, if you switch up the order of the buyer coming into the market, then you would actually get different outcomes of the market. So we want to avoid that. And thirdly, it's individual rationality. That means that in this context, for the buyers, they would achieve at least non-negative gain. And for the sellers, they have a certain revenue requirement, and those have to be met. And then finally, there is the computational tractability, meaning that we want to make sure that the model is solvable, it's convex, and also we want to avoid combinatorial problems, which I will explain in more detail later. Here is the general framework expressed in this diagram. It's a lot of information. So for now, I'm going to introduce every box individually, but for now, I just want you to pay attention to the gray boxes. On the left, there is a buyer. In the middle, there's a central data market operator, and on the right, there's a seller. To note that here, we can actually have multiple buyers and multiple sellers, but because just for simplicity, in the diagram, I'm only showing one of them each. So in the data market, in the first step is for the central data market operator to collect the data and also the actual task, which is in the form of a forecasting job in our application that the buyer decides and also the buyer defines. Here they have their own regression framework that they do for their own forecasting job. Again, in the context of wind turbine forecasting, they will try to forecast their generation. So they will use their historical data and also the weather measurements and so on to do a regression first and find the corresponding coefficients that would apply to their own data, and then do the forecast of the next hour or next day's generation. And then with that, they define a loss function, which usually is related to the error of the forecast. So here, most commonly, they like to use the mean squared error, which is defined as the difference between their target, which is y, and their forecast, which is x times beta. Again, x is the data they're using for the forecast, and beta is the regression coefficients. And they use the mean squared error, which is the L2 norm squared of this that represents the error in their forecast. And here we add a term called the willingness to pay, which is the phi number, and that represents their value they place on this forecast, meaning that the higher this willingness to pay is, the higher they value their accuracy of the forecast. And reversely, the higher number the willingness to pay is, the higher they value the improvement in this forecast. And because their goal is to minimize their mean squared error, here they just do an ordinary least square regression on their own data. So they get the beta values of their own and also the x values of their own, and they define their loss function and advertise that to the central data market operator. That's the first step. Second step is for the market operator to collect data from sellers. Here, the sellers offer data in different formats. First of all, there's the raw data in different types of features. This could also be their historical power measurement, also the weather measurement, and so on. And another value is the reservation to sell, and it's similar to the willingness to pay from the buyer's perspective. This is kind of in reverse, where the higher the reservation to sell is, the more unwilling the seller is to disclose their data to the buyer. And that is related to their revenue threshold, which says that if this threshold is not met in their payment, then they would not be willing to disclose their data. And usually there's some direct association with this revenue threshold and also their willingness to, their reservation to sell. We can, for example, define it as the L1 norm, or the absolute value of the product of the reservation to sell and the corresponding coefficient of their feature. And remember that here we haven't done the regression with the seller's data, so this coefficient corresponding to the seller's data is still unknown. But it makes sense, because the higher that coefficient is, it means that more correlated their data is to the buyer's task. So the seller would, be willing, would want to be paid more because of that. And then the next step, the third step, is for the market operator to redo the regression with the seller's data, given the buyer's analytics task in the form of the regression. Here, when they update the regression, of course, the thing that they're updating is the coefficients, including the buyer's features and also the seller's features. And eventually, after the update of the coefficients, they can update the buyer's losses. Hopefully, this loss will be lower than their original loss, given additional data from the seller. So because loss function is defined by the buyer themselves as in the form of a mean squared error times their willingness to pay, the central data market operator has to respect that. The difference here is that they're going to have more data from the seller, so this loss would be reduced. But remember, when the buyer is doing their own regression, they use the ordinary least squared regression just to minimize their own losses. But for the central data market operator, they don't have to use the same regression. They can use whatever regression they want to use as long as they can reduce the eventual losses of the buyer. And here is an example. If they use Lasso regression, they would just add a regularizer in the regression framework, which is the product of a factor and the L1 norm of the beta values. And of course, they can use other regularizers. They can use ridge regression as well. And then the fourth step is for the data market operator to collect the payment from the buyer. Now, this payment obviously has to be lower or equal to the reduction in their losses to make sense for the buyers to even participate in the market. Otherwise, it would not be worth it for them to even submit their task to the market just to get a loss from the market, right? So this payment is limited by the difference between the two loss functions. And then final step is for the central market operator to distribute the payment to all the sellers. Again, to remind you, there is some market properties that we would like to satisfy. The first one being the balanced budget, meaning that the buyer's payment has to be equal to the total revenues of the sellers, so that the central data market operator could stay nonprofit, and also they won't suffer a loss. And second of all is the individual rationality, where the revenue has to be higher than the individual revenue threshold that is set by the sellers themselves. So after explaining the whole process of the market, now I'm going to focus on the final step where the payment allocation takes place and discuss different ways of doing that. First of all, we're going to look at some cooperative game theoretic frameworks to distribute the allocation. Specifically, we're going to look at leave one out and the Shapley value. To define this in a cooperative game framework, remember that there is a loss function that is defined by the buyer, and they have already conducted their own regression using their own data. So the loss function of their own data is defined in L1, Li. And then with the seller's features, in addition to their own features, the market operator would redo the regression. So now the regression has been updated to LS. And if we define the set of sellers as where this S represents the set of sellers, which is the coalition of all the sellers within that are participating in the market. So now remember the total payment upper bound would be the difference between the two loss terms. And if we define the difference between the two loss terms as the value of this coalition of sellers, and here because the S represents the total, every single seller that is participating in the market, we can call this the value of the grand coalition. And if we expand that to any subset of the grand coalition, meaning any combination of the sellers in the market, then we can expand the value function to all kinds of subsets of the sellers within the market. That would, so for example, this term would mean that for all the sellers in the coalition J, the value of that coalition would be the difference between the buyer's original loss function minus the new loss function using the data from every seller in coalition J. And here you can see if J equals an empty set, meaning that there is no seller that is participating in the market, that means that the loss function would remain the same as the buyer's loss function originally. So the value of the empty set would be 0. And first allocation method is called the leave one out payment. And this is very simply defined. It's just the difference between the value of S, which is the value of the grand coalition when all the sellers are participating, minus the value of the grand coalition without the specific buyer J. So that would be the payment for this buyer J. You can consider it as the marginal contribution of J to the buyer's payment function. Sorry, not payment function, but to the buyer's loss function. So with the advantage of this method is the computation tractability. It's very simple. You just have to calculate 2 values and take the difference of them to calculate the payment. But the problem with it is that it's not balanced. It doesn't have a balanced budget. One simple example you can think of is if you have 2 sellers that have identical data, and now if you take one of the sellers out, then the remaining seller will still have the complete data set, and meaning that the marginal contribution of any one of those sellers would be 0. So the payment for both of the sellers would be 0 using this definition. But then if you add 0 up, it wouldn't equal the payment from the buyer, right? So now we can consider a different payment method. The most commonly used payment method in cooperative game theory would be the Shapley value. That is still based on the marginal contribution of each player, but instead of only looking at the marginal contribution of the player in regards to the grand coalition, now we look at all the subset or all the coalitions of the seller, and then take an average of the marginal contribution of that player to these coalitions. So the advantage of this is that it guarantees a balanced budget. And also, along with that, it guarantees certain fairness properties, including the symmetry, which means that for 2 identical sellers, you will get the same payment. And also 0 element, that means that if a seller has absolutely no useful data for the buyer's task, then they would also receive 0 payments. Again, there is another caveat for this Shapley value, which is the computational intractability, because now if we want to look at all the coalitions within the market framework, then that is 2 to the number of sellers. And once you increase the number of sellers, this can quickly become intractable. And secondly, it does not really guarantee the revenue thresholds being met. If you remember, we have, as we were going through the payment allocation, we haven't really talked about how the revenue threshold is being met. And if that's not considered, then likely there will be a scenario where after you calculate the Shapley value or leave one out, you realize the payment does not really meet the revenue threshold of the buyer, of the seller. In that case, the seller would say, okay, since you're not paying me enough, I'm now going to retract my data from the market. And what happens then? The central data market operator would have to redo the regression of the remaining sellers and see if that payment eventually would also satisfy the remaining sellers' revenue threshold. If that doesn't happen again, then the central data market has a combinatorial problem, because it has to look at all the combination of the sellers in the market to see which combination would actually produce a result that would satisfy every seller. So this becomes intractable as well. To solve this problem, we looked at the payment term again and tried to come up with a different payment allocation. So Lasso is what we came up with. And here Lasso stands for least absolute shrinkage and selection operator. And if we go back to the the beginning and to look at what the market operator's objective is, we can define it as to maximize the data buyer's gain while meeting all the data seller's revenue requirements. So now not only the revenue requirements are met, but also the data buyer's gain is maximized. So if we bring up the loss function of the buyer again, this is the loss function of the buyer with all the seller's data. And now the total gain of the buyer could be defined as their original losses. Well, here pay attention because it's not the difference between their original loss and the new loss function, because consider they're participating in the data market, they have to pay into the data market as well. So they should be, their overall gain should be the difference between their original loss minus the sum of their new losses and the payments that they're giving to the data market. What does that mean? So now if we want to maximize this whole term, remember that their original loss is predetermined. That is a fixed value using the buyer's own data. So instead of doing the maximization, we can just do the minimization of the second term, the term within the brackets, which is the sum of their new losses and the payment to the market. And if we bring back some of the assumptions that we made earlier, we had assumed that the budget balance would be satisfied. So the payment has to be equal to the sum of the revenues of the sellers, right? And then secondly, since the revenue of the seller, of each seller, has to be higher or equal to their revenue threshold, then the easiest way of doing this is to set the revenue, to be exactly the same as the revenue threshold. And we have already defined the revenue threshold as the L1 norm of the product of their reservation to sell times their corresponding coefficient. So now we can replace this payment term with this L1 norm. So using this chain of kind of equation, now we have replaced the payment term as the sum of all the seller's revenue threshold, which is expressed in the reservation to sell and their corresponding coefficients. And if we write that in the matrix format, it's a diagonal matrix and their payment and their beta values. Now we put it back into the original market operator's objective function. Now it has become to find the coefficient matrix that would minimize the sum of the buyer's losses and the payments of the buyer to the sellers. So this is actually a Lasso regression in itself. And the Lasso term here would directly represent the payment to the sellers. And of course, here to say it's a Lasso regression is a little bit inaccurate because the Lasso regression, the original form of the Lasso regression has a uniform lambda value outside the L1 norm. But here, since we have different sellers, we give the sellers the freedom to define their own reservation to sell, but it doesn't really impact the computation complexity. And what we essentially did earlier with the Lasso payment is we had combined step 3 to 5, where from updating the new regression coefficients to collecting payments to distributing the revenues into one step. So now the central data market operator, all they have to do is to solve this Lasso regression model and get the payment values from the buyers, which is the sum of all the revenues, and also to get a Lasso term to be equal to the revenues that the sellers would receive. To summarize, compared to the post-regression payment allocations, that's referring to the earlier game theoretic payment allocations, that was just one type of post-regression payment allocations. And when I say post-regression, that means that you do the regression, if you go back to the previous slide. So when the central market operator does the regression first, update of the regression first, and then collects the payment and distributes the revenue, that is called a post-regression kind of allocation of payment. But here, the Lasso regression actually is a way of doing the regression and the payments all together. So compared to the post-regression regression payment allocations, using the Lasso term directly as the payment would guarantee, first of all, the revenue thresholds of the sellers. And then second of all, it would maximize the buyer's overall gain. And third of all, it would also avoid solving combinatorial problems. So in other words, it also guarantees the computational tractability. And we have written this work in the following paper, and this paper has been accepted to PSCC, and we'll be presenting it also at the PSCC conference later this year. I see that we still have some time, so I'm going to go through the case study results. And again, these are very preliminary results. It's just kind of a proof of concept. We haven't really used, obviously, data markets haven't really been applied anywhere, so you'll see. First of all, we did some synthetic data. We simulated 5 different players using time series data, and player 2 to 5, they all have an autoregressive data. They're all independent of each other. And then player 1, we simulated it to be correlated with other people's data. So now going through the data market, we can see if we increase the training time, that is, I guess I didn't really explain this that well earlier, but the training time actually represents the length of kind of a feature that you would provide to the market for them to do the training. In time series data, for example, if you're doing 1 hour ahead prediction of the power generation, then you could provide, say, like the last 3 days data, or you could provide all your historical data and train that data based on a certain lag, which means that you can say, I'm going to use a window of 3 days or use a window of 2 hours to train to see what actually is the corresponding coefficients for those 2 hours in terms of the forecasting ability. So if we increase the training time, normally you would have better forecast. Of course, if the data is non-stationary, that might not be true. But here, since we have assumed a stationary correlation, then the longer the training time is, technically the more accurate the coefficients will be identified. So here, what is shown here is the profits of all the players. In the first figure, with central player also being the buyer, is player 1. They have correlated data with other players. So as you increase the training time, you can see that the correlation between the player and the other players have been identified more and more, and then eventually the buyer would benefit from this framework because they're going to be able to use the other players' data to better forecast their own data. And you can see that for the sellers instead, their profits go up a little bit and then eventually they shrink down to 0. That is because the y-axis is showing the average profit per time step. Per time step, that means that if you increase the training time, remember earlier when the revenue threshold is set to be the product of the reservation to sell and the beta value, that does not take into account the training time. So if you want to talk about per time step, then that value, even though eventually it's going to be fixed at a certain value, eventually it's going to be shrunk down to 0 because you're increasing the number of training time to put the T on the denominator, essentially. And then on the second figure, when the central player or the buyer is an independent player, player 2 here, saying that their data actually has no correlation with other people's data. As you increase the training time, the market is going to figure out actually there's no value in other people's data to help improve the forecast of P2. Then eventually the benefit from the data market is going to shrink to 0 as well for P2. And of course, for the other players, since they're not going to give any payments to the market, then their revenues also shrink down to 0. And then we fixed the, well, first of all, we also expanded the case study to a more realistic case where we took Nord Pool data. Nord Pool is actually the market operator, energy market operator of the Nordic countries and Baltic countries. So we got some wind generation data from Nord Pool, and their data are by zone. So here we looked at Denmark and Sweden, and there are 2 zones in Denmark and there are 4 zones in Sweden, and we just used the aggregated wind power generation. Again, this is a kind of idealistic case. It's not in reality, people are gonna have way smaller wind assets as a competitor in the market, or they can actually have assets that are cross zones in the market. But just as a proof of concept here, we just aggregate each zone as one player, and we use Denmark zone 1 as the data buyer and the rest of the zones as data sellers. So now we fix the reservation to sell for all the data sellers, and now we fix the reservation to sell to a single value. So everybody has the same reservation to sell. Now we increase the reservation to sell for everybody together and look at all the sellers' revenues. As you can see, everybody's revenue kind of follows a similar trajectory, that is first increasing to a certain level and then dropping down back to 0. And how do you explain that? If you look at the payment value, again, it's it's lambda times beta, and you take the L1 norm of that. And when you increase the lambda value from 0, of course, the profit is going to increase from 0. And remember, when you're doing the Lasso regression, the lambda value is a regularizer. So what it essentially does is that when you increase the lambda value, the beta value is going to be shrunk slowly. And so you see this kind of upward trend, and eventually the beta value is going to be shrunk completely down to 0 as you increase the lambda value. So all the payments would increase a little bit and then eventually shrink down to 0. That's how you explain it. But you can see also different players would have different peaks and also have different shapes. That has to do with kind of the absolute generation of each player, and also their correlation, different correlation to the buyer. And here we instead of fixing the lambda value for all the players, we're picked out 2 zones, Sweden zone 1 and Sweden zone 2. And we looked at if we change their lambda values on different scale, how their profits would change. So on the x-axis, that's the lambda value, with the reservation to sell for Sweden zone 2, and then y-axis is the reservation to sell for Sweden zone 1. And on the figure on the left, it shows the profit of Sweden zone 1. And as you can see, the maximum profit is achieved when Sweden zone 2 has 0 reservation to sell, while Sweden zone 1 has somewhat of like a medium reservation to sell. But on the other hand, if you look at Sweden zone 2's profit, that actually happens when, again, also Sweden zone 1 has a reservation to sell of 0, but Sweden zone 2 has a very high reservation to sell. That just goes to show that for different players, there might be different optimal strategies in the market to set their reservation to sell to maximize their profit. So there might be a market equilibrium somewhere, but if we're only looking at reservation to sell as a measure for their revenue threshold, we can see that people can either use this as a kind of a benchmark of how much money they want to get paid, or they can use it actually to play the market and to maximize their profit in the data market. And that's some future work that we would like to explore. And with that, I'm going to conclude and talk about our ongoing research. From this work, we have learned that by setting up a regression framework for the data market, we can encourage data exchange so that we can improve the tasks of the data buyers while providing some financial compensation for the data sellers. And secondly, if we use the Lasso term as a payment, then we can guarantee the revenue thresholds being met from the data seller's perspective, and while maximizing the overall gain of the data buyer. Some ongoing research includes looking at out-of-sample payments. So far, we have been only looking at in-sample. Out-of-sample is a very troublesome and also difficult task, but that is something that we would have to go into if we want to actually have some realization of or real-world applications. And second of all, we want to see how we can set the reservation to sell as a market strategy to maximize the participants' profit. And lastly, this framework can be adapted to an online framework and also distributed framework to further guarantee the convergence and also the computational the computation the ease of computation in a real world application. So with that, I would like to conclude my talk, and thank you so much for listening. I know it's a lot of math and it's quite dense for this short amount of time, but I hope you guys got some out of it. Thank you very much. Oh yeah, questions are very welcome.